Hello, my name is Hashim Fauzi, and I am part of a group with Samuel Hurtado, Omar Hussein, Paul Seward, and Chin Mariam Mubnu. We're going to be presenting about recurrent neural networks. A short bit about it, we're going to be also presenting about the motivation behind recurrent neural networks, the theory behind recurrent neural networks, the common problems with them, and some respective solutions to how they can be solved, and also a bit of the theory behind it in terms of examples this time, and also a little bit about the definitions and some illustrations. So to start with, recurrent neural networks, they're basically a deep learning tool used in machine learning. They facilitate many things in terms of how they have the ability to predict other things using their process of looping through each and every single program that they go through, each iteration, and keeping the memory. They can save their predictions on the next layer, and as well as create loops with the error and the information generated using its gradient and backpropagation. And similar to various neural networks, recurrent neural networks use the training data that it already has been assigned in order to formulate its own theories. In addition, recurrent neural networks, they have the ability to input and decide a already fixed size determined beforehand, while recurrent neural networks themselves can take data of various length already inside of it. This is a big flexibility. It can allow many things, like for example voice recognition, which means that you can use like a very long paragraph versus a short sentence perhaps. But this may cause issues with every single case though, as sometimes cases with memory for repetition for the same task can be accomplished with recurrent neural networks. Also, additionally, in terms of parameters, recurrent neural networks work in that they can take the same layer of for every single weight. Every single the same weight for every single layer. Recurrent neural networks process this with every single weight that's moved, but through backpropagation. It determines using gradient descent, and it determines the gradient descent. Feedback is then given back, and then the algorithm then goes loops with the weights adjusted. Here you can see in the input the pressure, speed, temperature example that I've put here has been moved into the hidden layer while keeping while moving through a 1/4 and 1/4 all the way here, and then keeping the output into the, but before going and fully finishing, it stops and gives a feedback connection to the hidden layer, and then repeats the process again, this time with the information it has generated already. Now it can then make a more processed decision, and then after the backpropagation algorithm then finds a better sufficient gradient, output is then sufficiently processed and then given back to the user. Now for prediction, the largest beneficial recurrent neural networks show high value in their memory from the previous sequences and loops. This prediction is one of the biggest motivations behind recurrent neural networks, especially in time series data, and for language as well as for language important stuff. These can be provided and be more efficient to other neural networks. And backpropagation is why Again, spoken well, backpropagation is a conventional neural network need. And right now, recurrent neural networks are widely used, especially in Siri, image processing, and more. Here in this example, as you can see, lottery numbers have been included as like a joke, but it's sort of meant to show how predictions can be possible with this. Thank you for watching. I'll now move on to my other members' parts.
Hello everyone, this is Samuel here. I'm here to explain the theory behind recurrent neural networks. So first, I thought we would get a conceptual overview of what it's all about. So this is what I call a rolled up version of an RNN. So it kind of looks like a normal neural network if you think about it. You have some inputs going in. Some of those inputs one output comes out of that, and then it goes back into another layer, and then out comes something else. Looks pretty standard. The only thing that's kind of weird are these T's, right? So as it has been explained before me, recurrent neural networks work for sequential data. It could be time related, so we are going to talk about like time steps, but it doesn't have to be time related. It doesn't have to be chronological. It just needs to be sequential in some sense. But we're just going to say time step t plus 2 or time step t to make it a bit easier to understand. I think notation wise, it's pretty standard what's going on except for these h's. Just want to explain what those mean. So our input is always going to be x. This is our data that we're going to input into the recurrent neural network. However, these h's carry with them some information. So what they're actually called is current context, and basically they store the values of hidden units. Informally, we can think of this h as our memory for time step t. So again, we can see here we input these two inputs here, x and h, t, and out comes h sub t plus 2. So let's see what's going on there and unfold this part over here. If we unroll it, quote unquote, we'll get this. So this is an example where there's 3 recurrent layers, and then there's this normal feed forward layer. So what's going on over here? First, x and h are going in, and then out comes the memory h sub t plus 1. This is our next sequential input, which doesn't come from our previous layer here. It's just the next input. And then together with our memory from the previous layer, we input that again to the second one, and so on until we get this out. And then our last memory, or our last h, goes into the feed forward layer. And then out comes our final output, y sub t plus 3. Now, remember, we're still in supervised learning here. So say we had a sequence of points. So, I mean, I'm working with combinatorics right now. So say we had a sequence of integers, right? Say standard Fibonacci sequence. 2, 3, 5, 8. So we could say that we have inputs 1 over here, 1 over here, 2 over here, and then we're trying to predict what the next input will be, which, if all goes accordingly, will be 3. So y will be 3 if it goes accordingly, and if not, we have an error. And then these just like store the memory from the previous layer. All right, so the activation function f that we saw in here is the one that is in all of our recurrent layers, and it has 5 inputs: x and their weights, so the input at time set t and its weight, the memory h sub t and its weight, and then the bias. And then the way it handles them is just like multiply the weights by the respective variable, right? And then add the bias. And for the feed forward layer, again, kind of the same concept, just 3 inputs though. We have some weights, an input, and then some bias. So we multiply the weight by the input and then add the bias. Sorry, the bias here. And just so we're clear, we put it into an activation function G and an activation function F here. These can be any number of activation functions, which will be discussed later in the presentation. So how do we go about training them? What's the pseudocode or algorithm to train them? Well, first, we'll do a feed forward step. We set all our h's to 0, so all the memories are set to 0, and then we compute the values of all the hidden units for k time steps. Again, k is a hyperparameter, so we decide how many recurrent layers are in our network. And all of those steps are computed via the activation function f. And then the last layer is just like a traditional neural network, and we just compute the output with our activation function g. All right, and then to backpropagate, it kind of has a special name for recurrent neural networks. So it's called backpropagation through time, or BPTT for short. The way it works in summary, because I do believe it's going to be talked about later on in the presentation, is you unfold the network and then you just do regular backpropagation. And the way you do that is you just get the error. So this is our output from the network, and this is our expected value. So again, in that example I did previously, we expected it to be 3. Y sub t plus k might or might not be 3. And then we just get the error and compute the partial derivatives to backpropagate. Now, there is an important note here for backpropagation through time, and that's that as you increase the number of recurrent layers, the computation time increases as well. Why? We have seen that the more layers you add to a network, the more the computation time. So I guess you could use that as initial intuition, but I think there's something else going on here, and I just want to explain that. So intuitively, for backpropagation, we need partial derivatives, one of which is this one over here. Now, what's interesting about this is that h sub t is a function of the memory of the previous layer, depending on how many layers we have. So if we want to compute this derivative over here, we will need to compute the derivative of h sub t plus 1 with respect to the weights at some point, and so on and so forth. So I show that right here. Just let me go down here. So according to the chain rule, we would go on and on and on here, depending on how many time steps, sorry, not how many time steps, how many recurrent layers we have in our network. It's just something to have in mind whenever you're building a recurrent neural network. Just have in mind that the more recurrent layers you have, the more the computation time, specifically because of this. All right, that's it from my part. You can find some of the sources for the theory of recurrent neural networks within the slides. And yeah, have a nice day.
Hello everyone, this will be the common problems portion of our presentation on recurrent neural networks. Specifically, the largest problem to recurrent neural networks is the exploding vanishing gradient. Recurrent neural networks are designed to be able to handle sequential data, such as sentences, videos, and any other things that are also related to time series to predict. We can see as a sentence like, in the sky there are blank. A recurrent neural network could easily predict that based on the previous words. However, recurrent neural networks have troubles as these sequences become longer. The reasoning why behind this is going into the backpropagation and the chain rule behind it. As there's more sequences and timestamps in our sequential data, our gradient starts to expand larger and larger. I won't go through the steps due to time constraints, but we can see as the chain rule continues to apply, it eventually becomes the product notation of deriving a hidden layer with respect to the previous one. We can also look specifically at the weight matrix's involvement in this as we try to derive the gradient with respect to individual weights. The next slide might show this a little bit better. So the red arrow shows the backpropagation and how it goes through steps such as the activation function and how the continuous weight matrix then applies and then eventually goes through to the previous hidden layer. As this happens over and over and over again, the weight matrix becomes multiplied exponentially by a factor of t. And due to this, weights that are just only things like 1.5, when applied exponentially to a factor of something like 50 timestamps, which might not be the largest recurrent network, we can see that this reaches values that are in the billions. As these become larger and larger, what happens is that the step size also becomes larger during the gradient descent. This creates an unstable network as the learning cannot converge. But one thing we can do is we can cap the size of the gradient. This specifically applies to the exploding gradient problem. As we put a max on how large, and it'll be the norm of the gradient, it in a way will stop the gradient from becoming too large to be able to converge and limit the step size. However, it does not apply to the vanishing gradient problem. When we look at values that are less than 1, such as something like 0.5, when it is multiplied exponentially by a factor of 50, the scientific notation of that value is times 10 to the negative 16. And as this continues on, it will show a smaller and smaller step size. The weight parameters will never optimize because the step size is too small. And at extremes, it can be so small that our computers will register those numbers as 0, and then those weights will never get the chance to optimize. Some possible solutions to this occurring problem is our choice of activation function. A common one that we see is sigmoid function. And in the graph above, we can see the pink for the sigmoid, and we can see the black for the derivative. And we can see that the largest possible value for the derivative of the sigmoid function is 0.25. And as our x's become a larger magnitude in the positive direction or the negative in the negative direction, we can see that their derivative approaches 0. This contributes to the vanishing gradient problem. Another choice of activation functions that are common is the ReLU, and we can see that when the x value is positive, it's a constant derivative value of 1 because of this linear slope. This prevents the vanishing problem when our x values are greater than 0. Another option is the tanh activation function, and we can see that the maximum value does reach 1 and would vanish much slower. Other possible solutions are our parameter initialization step, and then we get into our gated options where we're changing the architecture of our recurrent neural networks, such as gated recurrent units and long short-term memory units, LSTMs. In our initialization of our neural networks, this step can help us eliminate the vanishing gradient problem. Specifically, one option is the Xavier initialization. The Xavier initialization specifies that the variance of the outputs of a network layer should be equal to the variance of the inputs. There's different Xavier initializations based on the activation function, but the purpose of this initialization step is to center our values around 0 and, more importantly, close to 0. As we can see in our derivative graph, the values of x that are closest to 0 provide the maximum value, such as sigmoid's derivative of max value of 0.25 and tan h's derivative of around 1. Since the tan h function, using the input of its weighted matrix and the bias terms, will scale those values between 0 and 1 instead of 0.25, we can see the tan h function will avoid the vanishing gradient problem much more effectively. The next solution is the use of residual networks. We won't go much into those since those are something else entirely, but the use of skipping layers is important and kind of gets mirrored in how gates work. Specifically with residual networks is they allow skipping connections. This allows information to flow directly from one layer to another without being modified by the layers in between. It allows it to bypass the vanishing gradient problem by propagating the gradients directly from the output layer to the input layer without getting diminished by the intermediate layers. Next is the use of gates to help with the vanishing gradient problem. There are different types of gates with different notations and different sources. We'll call the gates different things, but the use of gates allows the network to control the information. Also importantly, it separates, instead of it being more of long-term memories, now we can have short-term memories and long-term memories as seen by this diagram. Here, the C represents the cell state or the long-term memory, and the A applies to the short-term memory, and often sometimes noted with the H instead for the hidden state. The long-short-term memories doesn't guarantee there's no exploding or vanishing gradient, but it does provide an easier way for the model to learn long-distance dependencies. Now we can backpropagate with uninterrupted gradient flow. The different types of gates can also be seen in the next diagram. The first one is our forget gate, applied with the sigmoid function, which scales the values between 0 and 1 when multiplied to the previous long-term memory, acts as a way of containing or gating how much of the previous long-term memory gets passed forward through this cell, 1 being all of it and 0 being 0% of the previous long-term memory. Next is the input gate, where the hidden state gets passed through the sigmoid and tan function, where the tan function applied will resemble a new memory, while the sigmoid function could represent a 0 to 1 or 0 to 100% of how much the new memory will be added to the previous long-term memories. So if 100% was the sigmoid value, or 1, then all of this new memory would get added, or a different percent going down to 0. Last is the output gate, where the long-term memories now can be outputted to new short-term memories through the use of the tan function again as a new short-term memory being multiplied by the sigmoid function, scaled as almost a percent of what this new short-term memory will be added in.
Hey, so I'm going to be talking about recurrent neural network architectures. So the first type we have is one-to-one, which is also known as the vanilla RNNs. They act as traditional neural networks, but they're actually recurrent neural networks. They allow a single input and give out a single output. So they can be used for image classification, for example. So for image classification, you can feed the network a picture of a couch and it's gonna classify that it is a couch. Secondly, we have the one-to-many, which allow one single output and can give several outputs, and that number of outputs can be different depending on the network. One-to-many RNNs are used for music generation or image captioning. So for example, for image captioning, same thing. If you put a picture of the couch, it's gonna give a caption about the couch. It's gonna say that this is a black couch sitting in a living room, and it looks beautiful, for example. Thirdly, the many-to-one. So the many-to-one allows several inputs and gives out just one output, and it can be used for emotion detection. So for example, if you feed the network words saying like I've been crying all day because my dog died, for example, it's gonna like the network is gonna give you what emotion this is, like sad or depressed, for example. Then we have the many to many, which allows several inputs and can give out several outputs. But and the thing is that with the many to many, you can feed the network like 50 inputs and get back 100 outputs. You can feed it 50 inputs and get back 20 outputs. There's no single like number, like it doesn't, they don't have inputs and outputs don't have to be equal. Depends on the network and depends on the problem. So as for the activation functions of recurrent neural networks, there are three main activation functions used for RNNs: the sigmoid function, the tanh function, and the ReLU function. So for the sigmoid function ranges between 0 and 1. It's the best function used for predicting probability, since probability also ranges from 0 to 1, so sigmoid is mainly used for predicting probability. One of the drawbacks of the sigmoid function is that it has a slow convergence and it's considered computationally expensive as it has e to the power of z in its function. It's also differentiable and monotonic. Tanh function ranges between 0 and 1. It's also an S-shaped function. It's best used to classify between two classes because it's any classes over 0, then it's in the class. If it's under 0, then it's in the other class. It's also considered differentiable and monotonic. One advantage of using the tanh function over the sigmoid function is that the tanh function is zero-centered, which makes it better, more optimal, and faster. It's still considered computationally expensive as it also has the e to the power of z, but it has different uses than the sigmoid function. As for the ReLU function, the ReLU function ranges from 0 to infinity. It is the most used activation function in the world, especially in the deep learning. It does not map negative values, so any negative value automatically turns into a 0, but any positive value can strike from 0 to upwards. It has faster convergence than the sigmoid and the tanh function, and this is because the ReLU function has a fixed derivative. One drawback about the ReLU function is that the value of positive inputs can go very high, which may lead to computational errors.
Hello, I am Francis, and today I'll be giving you a quick walkthrough of coding examples on how to use recurrent neural networks. What are we doing today? Today we'll be using recurrent neural networks to perform sentiment analysis of movie reviews from the popular movie website IMDb. Let's dive right into the code. As you can see from the screen, we perform our inputs. Kerat provides a dataset of IMDb movie reviews, and as such we perform an import by importing IMDb. We make sure that our TensorFlow version is 2.0, and then we load our data by calling imdb.loaddata. imdb.loaddata splits our data into training and test sets, but the data is split into 50% training and 50% test. I needed an 80% and 20% split. I decided to join the data again and call train test split to return an 80% split for training and 20% split for testing. I needed the validation data too, but calling train test split on the training data to give me a validation set returns an error of too many values to unpack. I decided to do the splitting manually myself by slicing through the values. So I sliced 80% of the training data and assigned it to the training data. Then 20% of the training data was assigned to the validation data. As you can see, once we print the shapes of the training, test, and validation data. We have 32,000 for training, 10,000 for testing, and 8,000 for validation. Let's see what the training data looks like. It's just a bunch of numbers, an array with list of values. So the data has already been pre-processed. That means we can run it quickly through our model. But wait a minute. If you run the dataset through the model, you're going to get an error, as the data is still of variable length, and neural networks need a fixed length of data. So that's why vectorization comes in. Vectorization helps you convert your variable length data into fixed length data to be able to feed it into the neural network. So we use the Keras tokenizer library with max number of words set to 20,000. This parameter was already set at the top after loading the data. And then we called sequences to matrix on the tokenizer to return the training data and the test data and validation data. And now we convert our list to NumPy arrays. This portion is very important. Why? Because if you do not convert from list to NumPy arrays, you're going to get an error of unable to convert data to tensor. So our data has to be a NumPy array. And path sequences, as you can see from the description, helps you transform a list into a 2D NumPy array of shape. Finally, we passed our data to the models. We created an input layer that takes the shape of the training data. And then we added an embedding layer that takes the max number of words. Finally, we added the long short-term memory model. You must have heard my teammates talking about the LSTM model. This layer is where the recurrent neural networking takes place. You can also try out another model, the simple RNN layer, and it gives you the different results. Finally, we add a dense layer with one neuron to give us our prediction. After running through the model, we get an accuracy of 0.50. Now, this accuracy was very poor, and there's a lot of things that could have been done to this data to improve the results. We could have tried another optimizer to see if we could get a better result, but this took a lot of time to actually process, and it's something that we can also explore for the future. Thank you very much for listening to this code walkthrough. Have a wonderful day.